In late 2019, there was a virus outbreak in China. Most of us remember it through memes. Little did we know it was going to get way worse. I mean, way worse.
The health authorities have activated their most serious response level
after an outbreak of a new type of viral pneumonia
in central China.
Symptoms included a rapidly growing cough that eventually turned into pneumonia. The virus has now become to be known as coronavirus 2019, or COVID-19 for short. The 19 being for the year of first contact, which was 2019. COVID-19 was traced back to a wet market in Wuhan, China. Out of the 41 initial cases, 27 of them had reported being there at a certain point, and while the rest is a closed case. As of today, the virus has infected over 4.71 million people, with an estimated recovery of 1.73 million people worldwide. As a solution, we made a computer-simulated model. No, not these models. The old meaning, which means the generation of physical, conceptual, or mathematical representation of real phenomena that is difficult to observe directly. The model we use, which is the SIR model, which is used by epidemiologists worldwide, is a group of differential equations which simulate the movement of people from infected and removed being either deceased or recovered. The average person with measles infects between 12 to 18 people. This number is referred to as the basic reproduction number. The R0 of coronavirus is between 2 to 2.5. On the other hand, the seasonal flu has an R value of 1.3. After 10 cycles, it leaves 56 sick. Coronavirus has an R0 factor of 2. This may not seem like a lot, but after 10 cycles, it leaves a staggering 2,047 people sick. And now for the simulations. In each square, we have a different number of the society's social distancing. We have 100% of social distance, 90%, 70%, and 50%. And we will now observe what happens over time and the number of people who eventually be infected. Right, so within our code, there are three major elements to consider. There is the node, the zone, and the universe. A node essentially represents a human being, and it has a status, and the statuses are divided into 4: susceptible, infected, recovered, and dead. And at any given time, a node can be either one of these. There are some values here that we assign to certain variables that we'll later use within functions. And in order to simulate the movement of each node, we use trig equations, with the hypotenuse being the speed and the different angles being the direction and the radius. So as you can see here, we use the math cosines and radians to take this. Nodes exist within zones. A zone is a certain distance that a node can exist within. A zone essentially represents a cluster, an area, such as maybe a town, a city, or a homestead. And then a zone exists within a universe, the universe being the world as large. And within the universe, when you run the code, it iterates and maps all of the nodes at every iteration into a GIF. And you can open the GIF. Here we have an example of a GIF whereby the probability of infection was around 50%, or the R factor was around 50%. And when we're not necessarily generating GIFs, we can also generate raw data from our code, which will come in the form of a CSV or a text file. And as you can see here, we have the total susceptible, infected, recovered, and dead. And as it goes through the iterations, you can see that nodes are moving through iterations until the very end, when the virus ends and there are no more infected people. This is what you get when you run the code from the universe. After cleaning it up a bit, refining it, and graphing out the data, this is what you get.
can be used to represent major transport hubs in the world and connected using graphs. Zones can be mapped into the world and connected using graphs with weights, and each one representing the probability of one zone infecting another. Zones in this case are major transport hubs. Finally, we can monitor the estimated spread of the pandemic throughout the world. In this case, dots mark major cities and areas of settlement. In conclusion, what we did is create a tool that's going to be used in major decision-making processes for people across the world, governments and corporate entities alike. This will help streamline and inform their decisions and better plan for the future, and also for people also to be well sensitized well in advance. The reason why coronavirus spread as far as it did is, let's face it, we all undermined it. But now we have tools that can help predict how far a virus will spread and how aggressively it'll spread in those senses. And hopefully, going into the future, we won't be able to make these mistakes again. Coronavirus will come back again. It's just a matter of time. But this time we'll be ready and we'll be able to see the impact it'll have in our communities and societies, and we'll be able to preemptly prepare well in advance because we have the tools to predict how aggressive it's going to be spreading this time around.